Now, yeah. I don't know if it's better for Sven Bodo to unshare so we can see all of Jeremy's
Yeah,
face.
can do. Yeah, that's better. Okay, thanks everybody. So just a really quick commercial break before Bodo's talk. And it's about the Scottish Programming Languages and Verification Summer School, which is happening hopefully next summer in Glasgow. So iteration 1 of SPLV was at Strathclyde University 2019. That was a real physical summer school. Iteration 2 was in Edinburgh last August, and that was a virtual summer school which had over 200 participants, so it was very well attended and a lot of really exciting talks. Iteration 3 will be hopefully next year, July or August 2021, and it's going to be in Glasgow. The arrangements are still quite fluid, partly because we're a bit disorganized, partly because we're not quite sure what's happening with the COVID-19 situation. At the moment, we're anticipating it's going to be a blended, partly physical, partly remote summer school. We're going to have 4 speakers, and we know that at least one of them will be a speaker on system security with the Cherry framework. That's because one of the Cherry EPSRC funded projects is co-sponsoring the summer school. We're also hoping to wangle some money from SIXA, which means registration fees will be minuscule, if at all. We'll give you more details probably at the next SPLS meeting, but for the moment, just watch out for SPLV 2021, which will be hopefully in Glasgow, physically or virtually. Thank you.
Can I just say that there's a nice TV I just placed in the Gather.town area, which will show you a video with Jeremy in it advertising this. So if you interact with the TV, then you can watch this video.
Okay, cool.
And Bob, could I ask you to mute everyone who shouldn't be speaking?
I should unmute myself because I'm going to chair the session. So it's my great pleasure to present the speaker for the last session, Sven Bodo Scholz, who is a professor in the University of Nijmegen and the original author of the SAC programming language. And today he's going to talk about memory management on the GPUs, probably using some SAC. So we're all interested to learn about this. Please go ahead, Bodo.
Yeah, thank you very much for having me and giving me the pleasure to talk about something completely different. Nothing really verified, very pragmatic. It's all driven by performance. And actually, I'm shamelessly abusing here all the how should I say, the kudos that should go to my PhD student Hans Fiesmann, because he did all the hard work really behind this. Right. So let me give you a little bit of an idea. I'll try, to make it as interactive as possible. So if you hear something really provocative and you feel like you can't hold yourself back, please, just unmute yourself and say something or ask something or scream or whatever you feel you want to do. So what is this all about? This is all about essentially compiling an array language, a functional array language called SAC to GPU code. And we have been doing this for quite a while. And so for those that are not familiar with SAC, shame on you. But you can just think it's NumPy. It's very similar to NumPy. It's just hopefully a little bit faster because it is compiled all the time. There's no interpretation going on at any stage. So you have this array language, and from this array language, we generate GPU code, amongst other things. And we have always been reasonably good in creating multi-threaded code, which performs very well. And then we have, I don't know, 5 years ago, or more than that, I think, yeah, 5, 6, 7 years ago, we have created a backend to generate CUDA code. Right? And now, at first glance, you may think, oh, that's trivial, right? Everybody can generate CUDA code. What's the big magic about that? Well, actually, if you have a language which claims to be purely declarative, then this language doesn't allow the programmer to give any hints, right? So the language itself has to figure out what piece of code should actually go onto the GPU. And so we do all this, and then you have to figure out how you manage the memory, which arrays do you want to materialize in memory, and how do you transfer them to the GPU? How can you make sure that you don't transfer too often? So the first thing that we have learned the hard way, as you typically do if you try to implement things, if you don't optimize your transfer times, you're doomed. And in a way, this relates to Magnus' talk earlier today. When he was comparing these warm times to the cold times, and the cold times were really cold in comparison to the very hot warm times. And that is just because, if you have to communicate a lot between the CPU and the GPU, sorry, but you're screwed. In particular, if you want to compete with handwritten CUDA codes, this is really, really tough. So memory is important. Now, what has happened over the last couple of years since we have done this is that has been a lot of move, and I will solely concentrate on this entire transfer thingy into CUDA, right? So what has happened over the last couple of years, NVIDIA has created new platforms galore. Every year or every 2 years, they come out with a new design, right? And that means, and they are not shy, right? They change dramatically. They introduce new stuff. They propose kernel nesting, and then they introduced lots of new ways to improve your communication. So they have asynchronous streaming facilities, and then they have the idea of unified memory that portrays to you this vision, you don't have to care about this at all. You just allocate something, and if you need it on the CPU, it's on the CPU. If you need it on the GPU, it's magically there. And the runtime system will do it for you, right? So we were wondering, maybe we have to do something about this. Our performance on the GPU backend, for some examples, is really good, in particular, if we don't have to transfer a lot. But there are some kernels where essentially you have an innermost loop, and inside the innermost loop, you have to communicate at least once from the GPU to the CPU. And we never got reasonable performance out of this. So as you do, I said, I need to seduce a PhD student to look into this, right? So the first task he had seemed to be very simple, but the devil lies in the detail, is, figure out what models are there and how do they compare. So he went away and did measurements, right? The most beloved activity of anybody, measuring real stuff and trying to really figure out what is happening on the architecture. So here are the results. Let me take you through this. So you see 3 graphs here, and these 3 graphs have been done on 3 different architectures. Can you see my pointer? Okay, so this is the oldest architecture, the Kepler architecture. Here's a Pascal architecture, and the latest fab, the Turing architecture, right? They have changed the hardware. And one of the things that CUDA likes, or NVIDIA, I should say, likes to do is they introduce new standards, and then they try to backwards support them on all the platforms. But because the newer hardware has other properties, the behavior is slightly different. So let's look at the individual measurements. What you see here is simply memory throughput on a transfer from a host to device or device to host. And in the x-axis here, we have the sizes. That is the size of data that we transfer. And on the y-axis is the throughput. So the higher the value, the better we can hope that the faster we can hope the transfer to be. And you see, essentially, there are six curves here, 2 blue ones, 2 red ones, and 2 green ones. So the red ones refer to this magical managed memory where you only allocate once, and then, NVIDIA does the voodoo. That's what it says on the tin. And then we have the standard one, which is blue. That is synchronous transfers. And then we have the green ones, which are these asynchronous transfers, right? And the 2 curves, just one is for host to device, and the other one is for device to host. So it depends in which direction you go. But what you see here, if you just take an eagle's view here, then you see, well, for the old architecture here, it's asynchronous that is top. If you look here, that seems to be similar. And there's a stark contrast. You just look at the numbers. We're, twice as fast, bandwidth-wise, that is. So really, we thought, ooh, look, there's performance that we leave on the road. Let's see what we do. But if you look then down here, you see that the managed case all of a sudden performs poorly, and that is on the newest architecture. That's really weird, right? So at this point, it was the first point of disaster that you can have as a PhD student. It's no longer clear what to do, because seemingly it depends on the machine, on the GPU that you really want to use, what you should do. Oh my God. So what are we going to do now? Well, simple thing, right? Since we are generating code, we can generate code for all 3 versions. So then we could use some kind of machine learning driven or heuristics driven choice, depending on the architecture that we want to execute it on, right? So here we go. But, well, isn't that just, flipping a switch, calling a different alloc that we need to do? What is really involved in creating different code for these 3 things? Right, okay, so let's start and look at this. So here we try to explain our reverse engineering or our semantics analysis regarding these transfers. So here you see the time going from left to right. Down here at the bottom, we have host memory, and up here we have GPU memory. And all we do is we assume that we start our execution on the host, because that's the typical accelerator model, and then we transfer the data that we need inside the kernel, which is the green arrow up here. Then we execute a kernel, which happens here. And eventually, after we have executed the kernel, we transfer the data back. Now, so we have 3 interactions, really. It's host to device transfer, kernel execution, and device to host transfer. And as you can see, if we follow the control flow here, we are executing on the host. We typically initialize some host memory if we have to, and then we may call a host to device. As soon as we do that, we deliver the control flow to the driver, right? And the driver will potentially do something on the GPU, but it blocks our main thread. So only when the data has been completely transferred over, where's my mouse here, at this point in time, then the control comes back to my host, and the host can continue doing stuff. Now, once we want to execute the kernel, this is an asynchronous operation. So the kernel starts doing something, but the kernel can't access, más o menos, can't access the host memory. For all practical purposes, can't. So that means fine. So the kernel is doing something on the GPU memory, and at the same time, the CPU can do whatever it has to do if we have some work that we can schedule on the CPU. Eventually, we come to the point that we want to transfer the result back. So this is this blue circle down here, right? Initiating a device to host transfer. Now, one thing can happen is that we ask for the result before the GPU is done, right? But that is handled by our driver here. So if this has not yet happened here, then it just waits here until the kernel has been finished. And then the transfer happens synchronously, all fine. So that seems to be simple in terms of code. Now, what happens if the host to device and device to host becomes asynchronous, right? So that looks like this. I have exactly the same scenario and the same kind of picture. Here we start a host to device transfer. That's fine. The host to device transfer is happening. But while the host to device transfer is happening, we can do something on the CPU. Oh, that's great. We can do latency hiding. Oh, that should give us good performance, right? Plus, from the previous measurements, we have seen asynchronous transfers have way bigger bandwidth. So we should be good, right? And then, yeah, well, ultimately, we have a kernel call here, the asynchronous again, and then we have a device to host transfer. It's all good, right? So, yeah, we just switch the mode, and yeah, life is easy, isn't it? Is it? No, obviously not. Why? Well, what happens if I want to do something with my host memory before the transfer is complete? Ouch! I have to make sure that I don't modify the host memory before the transfer is complete. So actually what I have to do is I have to synchronize if I want to do something with the memory. And because, you know, we do implicit memory management, we just have to inject a synchronization, GPU synchronization construct at the right point, which we can infer, but it just needs to be done. Yeah? Okay, and we have the same problem we have obviously on the other transfer, right? You know, if we want to access the data, we say, okay, give me the result back to the host. And then at a certain point, we want to read the data. But we have to make sure, we have to somehow know that actually the data has arrived, because otherwise we will just read some bogus values in our memory. So we have to introduce synchronizations there as well. And then obviously what you would like to do is to push the synchronizations as far back as possible to enable this overlapping of CPU and GPU activity, right? Okay, so that is doable, a bit painful, but doable. Now, what happens with this magic managed memory? How does it even work? Right? And obviously, CUDA will not tell you how it does work, really. It just gives you a couple of hints. So what really happens in managed memory is you allocate something and then you have a pointer. And you can use the same pointer in a kernel and on the CPU. Now, if you do this, internally, there are two buffers that are being handled by CUDA, and then the interface knows where the memory resides, but not as a one big chunk, but as individual pages. So if you ask for a certain piece of memory on the CPU, it will just make sure that it is on the CPU. And if it's on the GPU, it will just fetch it from the GPU at that point in time. Right? So it's kind of a pull semantics of getting the memory there. But now the problem is that you have to make sure that you actually don't access the memory, because you know you want to make sure that you don't do something to the memory before the kernel has been executing it. So actually it's not really a free lunch, right? It means, well, I have something here in my memory on the CPU, and I cannot modify this here. Because if I were to modify this here, then potentially the kernel would see wrong values. Ouch. Okay, so I have to introduce a synchronization here. First of all, I have to make sure that I never touch the memory, but I have to synchronize in the kernel as well. So here is, well, where's this? Well, yeah, so when I have launched the kernel at this point, and I want to do something with my host memory, then I have to say, oh, no, I cannot touch this memory now, because it's kind of the GPU's turn. I have to keep track of that the kernel is running. And at the same, I have to do the very same trick on the right-hand side of the computation as well, because I have to make sure that the GPU has finished all the transactions before I start asking or using the results here. So it is not just flipping the switch. It means you have to inject synchronizations, and you have to inject synchronizations at different points for different purposes. Right. This is all delight, obviously, for the implementer. That is, Hans had his fun in making sure that the injections of synchronization points are correct, and then stress testing it to make sure that he's confident that it does what it is supposed to do. So we thought, okay, now we are ready. We can run this stuff and see what happens, right? Okay, here's the first idea. I should have mentioned that before. I'm ahead of myself. I give you a little bit of an idea of the code generation. So let's assume we have identified where the kernel is here, right? This is the sec code. Then the typical code that we would generate is we allocate the memory on the host, we allocate memory on the device, then we have a host to device transfer, we have a kernel execution, and a device to host. This should have been device to host transfer, and then we free the stuff. Now, as I already told you, we have the problem that we have to inject synchronizations here between the host to device transfers and the kernel and the host to device transfer and the subsequent code. But we have to do something more. We have to actually what is called pinning. We have to pin the memory on the host. You may ask, what the poop is that, right? Well, what it does is it makes sure that your MMU in the CPU keeps that page alive, because otherwise the asynchronous transfer to the GPU may not work. Okay. Right, but that can be done. That's not too hard. And let's look at the managed code. And here you see the managed code in a way is simpler. We're only dealing with one variable now. Well, previously there was an A device and an A, and now it's just A. But that screws up our memory management, right? You know, aren't we lucky that our memory management is automatically injected by the compiler? So we don't have to really make any changes other than using the very same memory. That's great. And we have to inject these synchronizations. So after Hans had gone through this, he wanted to harvest his fruits, right? And off he went. So we took the typical example. We have a loop, and inside the loop, we need to have one device to host transfer to do something on the host before we decide whether we continue iterating. And what you see here, okay, you see runtimes relative to our old backend that uses synchronous transfers. This is one. And then you see here on the right-hand side, also quite interestingly, the sequential execution that has nothing to do with the GPU, right? But remember, one of the motivations was that we said, okay, these kind of examples are really rubbish with the synchronous transfer, right? Because they don't really speed up, because we burn all our benefits by just the transfers. And then you see our beloved asynchronous, what? Our asynchronous alloc is slow? Why would that be? You have potential latency hiding, and the bandwidth is better. And it goes on, right? If you do registered asynchronous things, that is with the pinning, it gets a little bit better. Okay, that's relieving, but the managed is also rubbish. Well, I'm not rubbish, but it's not really, you know, a reason to open the champagne bottle and, you know, anticipate a ready-made PhD or publication or anything, right? And then, you know, we look at a different platform and we see it's even worse, right? Our synchronous backend was great. So God, where did I send my PhD student to? And this is how he felt, right? And rightly so, huh? Because I don't know whether you know this feeling, but you try to do something, you think you have a good idea, you have a shot at it, and it really, you know, explodes in your face. So back to the drawing board, as we always do then. And we said, okay, what can it possibly be? You know, we know that the bandwidth is better. We know that we have potential latency hiding. So it can only have something to do with the allocation itself. Et voila. If you look at this, synchronous allocations are, you know, like milliseconds, whereas asynchronous is up to 7 milliseconds, right? And a big part of that is this bloody blue bar, which is this pinning. And the managed malloc is even worse. Okay, but then the thought was, well, but if I look at this loop as a human being, as a programmer, right? There's a loop, but there should be no allocations in the loop. Why would this matter, right? This is infuriating, but it turns out we do allocations in the loop over and over again. And that means essentially allocations that normally don't cost anything, really, barely cost anything. If we want to use this transfer technique, they become costly, and bloody hell, they kill our performance. Right? So at that point in time, Hans had to go back to the drawing board and develop an optimization to minimize the number of memory allocations. And he did. And we published a paper on extended memory reuse on last year's IFL, or the year before, I think. And if you leverage this with this new technology here, all of a sudden the picture looks very different, right? Now remember, here's the sequential runtime. All of a sudden, not only the synchronous benefits, but the asynchronous all of a sudden really starts showing its effects, right? The managed here doesn't show its effects, okay? Even with prefetching, if you tell, so you can do something with the managed that you tell the managed, okay, preload this, we know that we are going to use it. But that didn't help either here. If you switch to a different architecture, all of a sudden, we have a factor 5 faster code than the sequential code, something that we would have for this kind of pattern never, ever, right? So what's the bottom line of this? Well, the bottom line really is, it's complicated. The performance really depends on many things. It depends on what kind of GPU hardware you use. It depends on how the GPU is connected to the host. It depends on how your code really operates. So if you make too many allocations and we can't get rid of them in the loop, then you have to make a different choice than in the other case, right? So it is really, you have to look at memory allocation patterns and things like that as a huge optimization problem. We looked at possible cost models, but there are so many parameters, and these parameters have real, forgive my English, shitty impacts here, right? I mean, we are talking here, if you look back, we're talking here gigaflops, right? So 5 gigaflops is not the world necessarily, right? But if you get this wrong, it can be 1 gigaflop, which is a factor 5 slower. So I think it is most likely what we will need is we will need to have some machine learning based stuff happening in the background to make this a big story. But at least we now have the opportunity to play around with this and to have the compiler generate the synchronizations and maximize the overlapping of communication and computation of both host and GPU. I think that's roughly it, what I wanted to say. I shall mention once again, big kudos to Hans, who did all the hard work and allowed me to entertain you, hopefully, a little bit with these findings. And we are more than happy to collaborate and share on these things even more. Thank you.
Thanks very much. Let's thank Bodo. Are there any questions? The Zulips seem to be empty on the questions. So if anybody has any questions, please go ahead. And
I have a question. I raised my hand. I don't know if that was visible, but yeah.
Oh,
Not very noticeable, is it? Yeah, okay. So as interesting how you're saying how the memory allocators, well, very fragile.
Well, it's not really fragile. It is. It's just if you want to have real, blasting performance, then it becomes very volatile. Yes, you have to be very careful.
Yeah. So this is really comment and a question. Have you come across a new memory allocator called MIMALLOC?
MIMALLOC for GPUs or?
No, this is just for general CPUs. I don't know whether. So this is just something that was developed by one of my collaborators at Microsoft in a completely different setting. He's wanting to move. Well, he wants to implement a functional language without GC, but using reference counting. And as part of that, he came up with this new memory allocator.
Okay.
He apparently doesn't particularly know why it does so well, but it has already saved millions and millions and millions of dollars for Microsoft.
Okay.
Because
I mean, we have
just
our
performs slightly better in some ways. So I don't know. I don't know whether this suggests has any bearing on what you're doing, but it might be worth a look to see if any of the techniques he's using
No, thank you. I mean, we
relevant.
have been using reference counting since, I don't know, 30 years, and we have constantly outperformed non-managed languages on that. And we have a custom-made memory allocator too. So I definitely will look into this and see, how this compares to our stuff. But one of the things that you notice very quickly, if you do reference counting, you really want to make sure that you control the memory allocator, because the way the most memory allocators are just tuned for the C model of you allocate and then you garbage collect at certain intervals and you try to find this. Whereas in particular, if you have multi-threaded executions, you really want to make sure that you can do memory management without locks. And that, just if you use locks to do that, or if you have a stop the world garbage collector, you're just doomed at that point.
Yeah. Thanks. Well, maybe
Sure.
have a look at it. I've given you a link in the chat.
Excellent. Thank you very much.
And also in Zulip.
Yeah, Zulip is better because that's persistent, right?
Zulip should persist forever. Yes.
Whatever that means with computers, but
Any further questions, Bodo?
I've got a question I'd quite like to ask.
Yeah, go ahead.
sure, Paul.
Right, Bodo, I was wondering, does the managed memory, are you certain that it will lead an advantage for you, or you use it?
Sorry, you're breaking up. Can someone, if someone heard this properly, can you please relay it to me?
Well, I can try again at least once. I'm just wondering about the abstraction of the managed memory. You pointed out a few frailties of it. I was just wondering if you're certain that it will be worth pursuing. Do you think you will get a benefit from it in the end, or are you tempted not to use managed memory?
Well, if you look at these curves, which are just bandwidth curves, then you see that the managed ones are the red ones. So the bandwidth is typically, well, in some architectures, really, really good. And well, it has the advantage is if you think about the code, you have a kernel code and the kernel iterates and has certain arguments it iterates over, right? It may be the case that the kernel is not needing all the data. Right? You have an array and it may only read, say, 70% of the data, because it could be a sparse matrix and not all the values are actually being read. But we cannot statically infer which ones are read and which ones are not read. So in that case, you would really like to have a model where you say, okay, you just pull the data when you need it and when you really want to access it. Otherwise, you just leave it at the host.
Yeah.
So I think to translate this in the applicability, what this means is, yes, if I know that I need all the data, I would not even bother to look at managed. But if I know that I only need part of the data and I can't statically predict what data I need or don't need, I may consider doing this.
Okay, thanks.
Sure. Thank you for the question.
No problem.
I guess it's pint o'clock.
Is Artem, are you still there?
Yes. Maybe I'll ask a quick question. So can you quickly summarize what exactly has been implemented in Stack right now? So what can be used and what?
Oh, you can use all three of them. So at least in Hans's branch, which we hope to merge in over the next couple of months. You can just provide a compiler flag and say, okay, I want this to be using asynchronous communication, or I want this to use managed. And then the code is being generated with all the optimizations that follow. And I think this is also an interesting aspect with respect to the managed memory, because as soon as you have managed memory, you no longer have this explicit distinction between the two memories. So at that point, it might be interesting to see whether there are other effects on the overall memory footprint. Because all of a sudden, it might be the case that we need less memory in total.
All right. Yep. Thanks.
Thank you.
I guess, yeah, let's thank Bodo again. And
Thank you.
And probably this concludes today's this SPLS meeting. We might have some organizational questions which we can discuss either here or on.
Well, I think the main one is who's going to run the next meeting. And looking at the list, the expectation, I guess, would be Strathclyde.
Probably we can turn the streaming off because that's not very interesting.
Yeah, that's true.
Okay, I'll turn the streaming off.
Right.
There we go.
And oh yeah,